So what's the plan for today? So, by the way, I don't understand where is everybody. You know,
it's your students who are missing.
Yeah, should be. We'll see what we'll do about them. And if they חשבתי אם אני כבר מעיף אותך מהמעבדה או לא.
אחרי יום חמישי האחרון, כל פעם אתה עושה לזוז אותי מאיזון מחדש.
אתה אומר, אוקיי. אם חוזרים על בדיחה כמה פעמים אולי לא בדיחה, אבל לא.
היי!
פעם שלישית גלידה.
תצטרך בסוף איך באלברט ולצייר.
אתם יודעים מאיפה בא הביטוי פעם שלישית גלידה? מה?
כן.
Third time I'll scream. ויש עוד כמה כאלה. יש גם כל מיני וריאציות מגרמנית. אני מנסה להיזכר.
בירושלים יש שכונה הר אדר, ששם היה המקם הבריטי, רגאור הל. אז זה נהיה הר אדר.
כן, גבעת הרד"ר. Okay, so the plan is we're going to talk about two things that are related. One that we started last time, that would be squeezed states and a little bit of analysis for squeezed states and squeezing operators. Like things like properties in the sense of noise and things like this. Mostly things that relate to the noise. And we'll discuss the main thing that this is good for, and this is for optical interferometry. Which, as I told you, is the only way we know how to measure anything precisely. Really, anything, any physical quantity that is measured precisely is done by somehow transforming the quantity that you want to measure into an optical phase, which you can measure. So, and here, we'll say a few things about LIGO, just because it's interesting. We started talking a little bit about LIGO before, which is the largest interferometer in the world, and how squeezing comes into LIGO in order to improve its performance. And they are now operating LIGO with squeezed light, and that enhances or reduces the noise level, which means that it allows them to see even weaker signals that would normally be buried in the noise, not in the news. They have an improvement of something like 40%. Now, you could say, reduce the noise by 40%. Well, let me ask you, if I'll give you an increase in your salary of 40%, would that be considered like 40%? And in terms of measurement, that's exactly what it is, because that means that you can measure signals that are twice. And if you think specifically when you're measuring gravitational waves, then that means if your sensitivity is down, is better by a factor of 2, that means that you can identify signals that are square root of 2 more distant, which is, so you have something like 40% increase in radius. But in terms of volume that you can sense, then this is to the power of 3. So you gain. So it's square root of 2 to the power of 3. How much does that come out to? So something like a threefold increase in the volume of events that can be accessed. So it's something that's worth investing in. So I think that we want the air condition to work. At least I do. Not on 15 degrees.
אמרת במרצה קודם שזה לא משנה, למה למדנו את החומר הזה?
What?
אמרת לנו
No, that's not what I said. You got me wrong.
הצינור מביא מים קרים באותו טמפרטורה.
No. This will be part of the test.
כן, אבל יש הקלטה. אתה מוקלט.
That's not what I said. You got. What? Let me explain. I don't know.
תשמע, יש לך הקלטות עכשיו של כל הקורסים וכל הדברים. אומנם חלק לא מרצים זה.
כל פעם יצביעו קורס אחר להעיף.
גם יש איכות ויש חוסר איכות, נגיד. פה זה הכיתה הכי שווה. לפי יוסי. יוסי, אתה שומע, יוסי? סטטיסטית, הוא אמור להיכנס עכשיו, נכון? זה השעה.
What I told you is that the water is decided by the building, whether it's cold or warm. But you have the ability to decide how much you exchange heat with them. I mean, it's the operation of the fan inside, or how much it acquires air from the... So no, I mean, you have... The water is your heat reservoir or cooling reservoir, but you can locally decide how much heat you take out of them or back. Well, yeah. And that's what I was saying from the beginning. You didn't understand. Okay. So, what? What? כן, בשבילך יהיה מבחן. Okay, enough. Enough with all these jokes. We have things to do. Okay, so we said a few things about. So we actually discussed the parametric oscillator. So not oscillator, the parametric amplifier. We understood what it does. It's parametric amplifier takes an oscillator. In this case, the oscillator is the electric field, and shakes its parameters. For example, and as we said, let's think for a moment about an oscillator, a mechanical oscillator. Then a mechanical oscillator sits in a well. My head is the oscillating thing, and this is these are the walls of the potential. And all that the parametric oscillator does, or amplifier does, is shake this. Shake the walls from shallow to deep, or to steep, and shallow again. Or, as we were talking about, if this was a pendulum, you just shake the length or the height of the mass up and down. Now you do this periodically, and if the mass is sitting on the ground, meaning at the ground state, as in this case, then just doing this wouldn't shake anything. But if I am already here a little bit, then lifting this hand up will give some potential energy. That will cause the oscillation to the other side to go further down. And then if I do this thing again, it will increase the oscillation. So it can amplify the oscillation if the oscillation is timed with the periodic parametric change in the oscillator. Now, what would be the effective potential for the electric field? Then the answer is basically it's, then it has to do somehow with the index of refraction, or but so indeed we need some effective interaction with medium in order to do this to an electric field. The electric field oscillates in time, but also in space. So the oscillation, if I want to see the oscillation I need in time, I need to run at the speed of light within the medium. And I see this, this wave running back and forth over there. And now we need somehow, for example, that for some reason the index of refraction when the field is in the center, like near zero, or when it is, if the wave is, when we're saying that the wave does this. So whenever it's on the side, somehow the index of refraction is different than it is at the center. That requires some nonlinear response. That means that, for example, the index of refraction should depend on the intensity, because now the intensity is 0, and now the intensity is. So, really, it should somehow be dependent on the field. Now, and this is something that we don't exactly. I'm not teaching you how this is happening, but it does require some nonlinear response. Generally, parametric amplification has to do with something nonlinear in the medium. That's what causes the coupling between the pump field, which is the drive that changes the conditions for the amplified signal. Because in optics, indeed, what happens is that both of them are optical fields. This thing that does the parametric change is another optical field at another frequency. So yeah, we need, when you think about the pendulum, it's simple. Well, yeah, there's a motor there that changes the length of the pendulum, and the mass down underneath starts to oscillate because of this. But in our case, all of them are optical fields. We need something, the oscillation that we want to amplify is hundreds of terahertz in frequency. So we need a motor that runs at twice that. So if you operate, so that means that, you have an oscillator at 300 terahertz, and you need a motor at 600 terahertz. So this motor has to be some other electric field. And this other electric field somehow couples to the other one through a nonlinear interaction between them. Actually, what you need is some form to multiply them together, because this is what you need. So you need something that will do this. I have E pump, which is operating at has some amplitude times cosine omega pump t, and omega pump equals approximately twice omega signal, because as we mentioned, the parametric amplifier has something like this. And now, so we want that E signal as it comes out of the medium. So I'm talking about, I have a medium coming in, and there's E signal coming in here. Something happens to it, it comes out. And what needs to happen is that it will be sum of itself. So something, a number that is close to 1. It wouldn't be, you know, there should be maybe some conservation of energy. I don't know. There should be some kind of an, no, let's not call it A. Alpha plus beta. So this has to be something. And something small that contains whatever it is times the pump. Because this will do exactly what you need. What? Oh, so, okay. Ah, yeah, sure. The fact that those two fields are somehow, but this requires here is the nonlinearity. This means that something is modulated at twice the frequency. Okay, so that was as much as I'm going to tell you about nonlinear optics and the relation to squeezing. And now let's go back to quantum optics. So we understood, we said that what a parametric amplifier does is it takes, if I say classically that the field equals x plus iy, which actually means that E of t equals x times cosine omega t plus y times sine omega t. Then what happens for to the, if this is the input signal in, and the output, try to keep the same, put the in up. The output has, the x is amplified, and the y is de-amplified. Because this is what parametric amplifier does. But as we said, and what we said in the end of our last meeting was, okay, all of this is perfectly true, and well, if the field that comes in is quantum, then everything remains the same. It's just that these are the x and y operators, and this is the electric field operator at the output. Or if I want to talk in the terms of this, and this is a little bit, here we're talking about the slow varying amplitude of the field, which is constant, and here we're talking about the real field in time, which is oscillatory at the optical frequency. So please don't be confused between the two. You know what, let's call this the amplitude, the complex amplitude, and remind ourselves this is what we mean. And that means that there is, So we can say the following, that x, the operator x at the output is related to the operator x at the input. Whereas the operator y output is related to the operator y at the input. Relation. Is there a question somewhere?
יש עוד פעם להשיב.
Are you happy now?
הכי שמח בעולם שלי.
Okay. So this is what we said, and that means that basically, well, yeah, if this is the relation between the input and the output quadratures, then we can also write a relation, if we accept this, we can write a relation between the creation or annihilation operator at the input and the output. So the output annihilation operator equals, so x out plus I y out. And that is, as we see, x in e to the g plus I y in e to the minus g. And you can, and you can write this as being, this is what we did last time. And if we remember that x equals a plus a dagger, maybe divided by 2, maybe not, I don't remember. But eventually what you'll have, and if we put this back in here, then what we will have is a times hyperbolic cosine g plus a dagger hyperbolic sine g. Now, and that's the input. So in. Now what, I'll take it down because the dagger is up. So, and now the first thing to check is whether this is at all, if this at all makes sense. Is this a creation or annihilation operator at all? And then the question is, what are the states that it creates and annihilates? If it is a creation or annihilation operator, then what are the states that it creates or annihilates? So we're saying this A out equals, so now you know what, so now they have names, all of those operators. Let's call this A. No, I don't want that. We'll stick with out for now. Equals A hyperbolic cosine of G plus a dagger hyperbolic sine. Now we can ask ourselves, okay, what is this? A out dagger. Now that's easy to calculate. So we have this. I'm not going to keep all the, so it's A hyperbolic cosine G plus A dagger hyperbolic sine G times A dagger hyperbolic cosine G plus A hyperbolic sine G minus, well, the same thing with A dagger first. Okay, well, you can very quickly see that what we have here is hyperbolic cosine times the commutator of A with A dagger, and the hyperbolic sine multiplied by the commutator of A dagger and A. So this equals the commutator of A and A dagger times hyperbolic cosine plus the commutator of A dagger and A times the hyperbolic sine. Squared, right.
It's supposed to be a minus between them. Ah, no, you can flip them and that doesn't exist, right?
Yeah. And now this is 1. This is minus 1. Yeah. And hyperbolic cosine minus hyperbolic sine is 1. So the commutation relation is correct. This surprising transformation, which as I told you is a Bogulyogov transformation, maintains the commutation relation. So those are still creation and annihilation operators, even though they involve a mixture of creation and annihilation. This is, yeah. If it gives you a headache, that's what it should. So yeah, the fact that we take something like this, some mixture of creation and annihilation operators, even more so, the higher the gain, then it means that you take more of them. So like you take the annihilation operator multiplied by a very large thing. You take the creation operator, you add it to it, multiplied by nearly the same thing, almost the same. Definitely when the gain is high, and hyperbolic cosine and hyperbolic sine become almost the same. And you get something which, for some reason, still behaves as creation and annihilation operators. And so, first of all, okay, we'll see it in a moment, but ouch. Yeah. Okay. So first thing is that now we can already make all kinds of calculations. But before that, I'm wondering which of the two I want to do. But let me first explain something about how this transformation comes about. Okay? So you know already that in the Heisenberg picture, operators evolve in time. So in the Heisenberg pictures, the states are constant. Not that the wave functions change a function of time, but it's the operators that change as a function of time. And if I have an operator A at time t, it has a relation to the operator A at time 0, and it relates to it by this, minus IHT into the IHT. Do you know this? Yeah, you've heard that before. Now we have some kind of an evolution here. We have an output. What happened? We had an operator coming in. It did something. It evolved according to the Hamiltonian that occurs inside the nonlinear medium. This is what we want to understand, how it looks. And it came out like this. What's the Hamiltonian that does that? So I want to show you that we know something about this. So I want to claim that the Hamiltonian that does that is times, I don't know, some parameter chi times A squared or plus A dagger squared. I'm claiming that this is the Hamiltonian that does this. And let me show you that. And later we will understand what this Hamiltonian is. But you know what? Let's look at it for now for a moment. This Hamiltonian is something that involves either annihilation of two photons or creation of two photons. So this is something that involves pairs. This has to do with the fact that we discuss things that are nonlinear. So now I want to ask myself, well, what is? So what we want to calculate is this. So now I want to answer, what is this A of t, which is where t is the propagation time through the nonlinear medium, or in time is distance. So it has to do with. And that is, well, it's this. So e to the I chi t times a plus a squared plus a dagger squared times a times e to the minus I chi t times a squared plus squared. Now, okay. The point is the following. If this was, okay, this is the e to the I Hamiltonian. Now, if those two were commuting, then everything would have been easy, right? I would have commuted this with the entire exponent, and the two exponents would have annihilated, and I would have had just A equals A. Indeed, if you have an operator that commutes with the Hamiltonian, it doesn't evolve in time. But this does not commute with the Hamiltonian. So what do we do then? Now we use a very useful lemma that says the following. E to the b times a times e to the minus b equals what? A plus b commutator with a plus half b commutator with b commutator with a plus 1 over n factorial times the commutator b times b n times yeah. Exactly. Well, indeed. And if you remember something from analytical mechanics, which you probably don't, because none of you learned it with me. You did?
I did.
Yeah.
I did.
So you have seen already that you've seen Poisson brackets. And Poisson brackets involve derivatives. And the quantum analog of Poisson brackets is the commutator. Well, one more hole in your education to fill. That's what? No. It's because you came late.
Okay, yeah.
Well, I'm just, you know, if I'm giving a stand-up performance, then there must be someone in the crowd that I pick on, right? Yeah.
Oh, it's always me. It's
No, and then, so where are we? So now let's calculate this commutator. So this is going to be what? This is going to be A plus the commutator of, so what do we have here? We have I chi t times the commutator of A squared plus A dagger squared with A. And then we will have, let's just write the one next one, plus, or in this case it's going to be minus, of course, chi squared t squared times the commutator of A squared plus A dagger squared. No. We don't need that. Commutator of the same thing. A, and then there will be more. And here there will be minus I chi squared chi to the third, t to the third times the commutator, and so on. And we're missing a few factors, so there's a half, and here there's a minus 1 over 6, so on. Now, second one has minus. The third one should have a minus. This one also has a minus.
Yeah, but who cares? We throw them away.
What?
We throw them away.
No, the minus here is actually important. Okay, now look. What the nice thing about these commutators is that they very quickly collapse. What do I mean? Let's see, what's the commutator here? So A squared commutating with A is 0. So we only care about the A dagger squared. This is the only one that we care about. And A dagger squared commutator with A is just A dagger.
With minus, no?
What?
With the minus?
I don't remember.
Just makes sense.
Well, because the commutator, so here, so we're using this. So what we get here from, so A of t, well, equals, so let's see. Just you need to remember that A dagger squared with A, then the commutator is, well, you commute once A dagger with A. Well, you understand. This is A plus I chi t times A dagger, apchi. And then here what happens? This commutator is A dagger, right? We just calculated it. So this commutator is A dagger. So this commutator is A dagger. Now we commute A dagger with the Hamiltonian, with A squared. And then A dagger commutes with A dagger squared, so that doesn't change anything. And A squared gives us A A. So those commutators, and so this entire thing becomes A. And immediately you can say, just by the same thing, that this one is going to be a dagger again, and whatever is written here is going to be A again. So all those commutators fall down to being A minus I chi t A dagger plus minus half chi squared.
בטוח שהראשון כן מביא לך מינוס A dagger.
Doesn't matter. What? You need that mean that one needs to be minus?
Pretty sure.
I'm not. But we'll see in a moment, okay? Because we know where we need to get.
Yeah.
And then we yeah, so what we'll end up with so minus half this times A and then plus minus. You're saying that this one should have been a minus, maybe? No, I think that's okay. Minus I. What? Chi 3 T3 to the 3 times a dagger, and so on. Now then, and then we will have plus I. Sorry, not plus anymore. Now it's going to be plus. Let's write it like that. Plus half, not half. 1 divided by 4 factorial, chi to the 4, t to the 4 times a, and so on. Now you can see what? Okay, we have this a minus half, minus this half, plus this. Okay. We need something, but I'm going to correct this very quickly. Wait. We're going. So first of all, let's keep collecting things, and then we'll understand what. Okay. So this, by the way, is. Slow down. So this is like basically what we have here is a cosine, right? So this A comes out, and we have 1 minus half chi squared t squared plus 1 over 4 times chi to the 4 t to the 4. That's this part. And then there's this A dagger multiplied by, we have here, let's I chi t minus, yeah. So I can keep the I outside. We'll have this I outside, and chi t minus chi to the 3rd t to the 3rd over 6 plus and so on. And as all of you immediately notice, this is the Taylor series of cosine, not hyperbolic cosine, regular cosine. And this is the standard sine. So this is sine of chi t times I, because there's this I outside. And this one is cosine chi t. Almost. What did we do wrong? There's one thing that I missed. So let me write it here. So what we have now is A times cosine chi t plus I times A dagger times standard sine of chi t. So clearly this chi t should somehow play the role of the game. But why do I have standard cosine and sine and not hyperbolic cosine and hyperbolic sine? If chi was imaginary. Correct. This is the part that I should have said in the beginning. Chi should be imaginary. So the Hamiltonian we need to correct. How? We make chi imaginary, so just add an I here. Now there's a little bit of a problem. This is not a Hermitian operator. So now there's a... so we make this a minus. Oh, yes. And then everything is fine. So I'm sorry, but for all of you that watch us later in YouTube, jump the mistake. Because I didn't know it in the beginning. I didn't remember it in the beginning. But, what? I'm not going to check. That's the point. I mean, you confuse everyone all the way, and then everything would be fine, because hyperbolic cosine. No, I don't need to. You can correct it. It's just the same thing. So really, so that when chi is imaginary, then this becomes hyperbolic cosine of chi t, and this with the I becomes hyperbolic sine, and then everything's fine. And you know, indeed, all these pluses should be minuses. But for the commutators that we calculated, it doesn't matter, the fact that there's a minus here. Well, almost, come on. Don't be a nudnik. תודה.
וגם כן, העין למעלה באקספוננטים צריכים לעבור.
מה?
העין באקספוננטים צריכים לעבור, בסדר.
Yeah.
בסדר, לתקן את הכל זה...
You may make the corrections, everything works. Now, so we know, so we found what the Hamiltonian that generates this is. Now, let me try to explain what, first of all, I'll tell you what the Hamiltonian really is. And then I'll explain both classically and quantum mechanically why it works, why it actually does it. So there's our Hamiltonian. So I bluffed a little bit. The true Hamiltonian is this. Is indeed I chi times here. That's a nonlinear coefficient. And here, A pump. A dagger. Sorry, let's keep it the way it is. Oh. Or I'll explain in a moment. A pump dagger A squared plus or let's see, that would be alpha. Minus, and we'll keep here the I. A pump A dagger squared. This is, so as I told you, this has to do with a nonlinear interaction between fields. So actually there's this pump field, the one that does this. Now this pump field is a source of energy. If you create two photons or sorry, if you create two photons somehow, this Hamiltonian creates two photons, their energy should come from somewhere. Where do they come from? They come from the pump. The pump is the one that gives in the energy, and it will lose. So if two photons are created, one photon of the pump is annihilated. It also makes sense, because I'll remind you, this pump is operating at twice the frequency of the oscillators that we're looking at. So if the pump is operating at twice the frequency, then its photons are twice as fat. So if you break a pump photon in two, then the total energy is conserved. One photon of the pump is gone, and two photons of the signal are created. And in terms of total energy, the energy of the lost photon from the pump is equal to the energy of the two photons that are created in the signal. The same goes here, just the opposite. If the process is the one where photons are annihilated from this is the case of the decaying case. And if you're eating up photons, if you're annihilating photons from the field, you should be creating pump photons, and still the ratio is 1:2. So that explains why this is there. We have to say something about why should it be, and what about what just happened now? The answer is, let's assume that the interaction is weak. The interaction is weak, meaning this pre-factor of chi, the very small number. And then that means, and the pump, it contains a lot of photons. So the pump is a laser. It's a strong laser with a coherent state, probably a coherent state of a very large number of photons. Okay? So that means that the state of the pump, so if I can talk about the state which contains something on the pump mode and something on the signal mode. So this something is some state, psi s. I don't know what it is. But the pump, it's a very large alpha. And moreover, because this alpha is very large, if you add a photon to it or remove one from it, it doesn't matter much. So if you think about the case of an undepleted pump, which means that you can just replace this by alpha pump, and this by alpha pump star. And there we go back to what we had before. So now what I'm telling you is that really this chi that we had here and t and everything, so what we will have here is something, you have this chi here times t, whatever is in there. It is proportional to the pump field. Now let's call this is a nonlinear. Let's call this one kappa. Okay? I don't want to use the same letter just so that we. So I have here I kappa times alpha pump star a squared minus alpha pump a dagger squared. And indeed, so to discuss what we wanted to do would be to assume then that if alpha is real, then what we have here is times what we wanted, a squared minus a dagger squared. So let's not unmark this. this is the squeezing Hamiltonian. As we said, that we can, under a large pump intensity, we can replace them and then get to the... And what if alpha is not real? Actually, it's not a big deal. First of all, there are two answers to this. Well, you know, everything in optics is defined up to a phase. So let's decide that alpha is real, and that's it. We reset the phase clock according to alpha, and then everything's fine. And if not, what you will see is that instead of squeezing the, what we are assuming so far is that X is amplified and Y is de-amplified. You will very quickly see that if alpha is imaginary, purely imaginary, you will be squeezing X and amplifying Y. So the phase of the pump, phase of alpha, dictates which quadrature is going to be amplified and which quadrature is going to be de-amplified.
But you can't really move the phase of the alpha because you will also need to move the phase of A and A dagger. That's basically the point of alpha having a relative phase. It's the same thing. Because you define a phase relative to your entire system.
You have two solutions for this. One is to say, I define everything relative to the pump, and that means that alpha pump is real by definition. And that's it. And then I have no question. But maybe you don't want to do that. Maybe there is something else that already defined the phase equals 0, and you don't want to set this one as well. Because, for example, you have two parametric amplifiers, where one of them has one pump with one phase, and the other one has another as a pump with a different phase. And you then later want to check what happens when you mix them. For example, maybe you have two parametric amplifiers in a series, one after the other, and they don't have... Yeah, I assume that you have no idea what I'm saying.
Basically, what I'm trying to say that the relative phase between alpha and A basically decides the angle with which you're squeezing.
Exactly. Agreed. Correct. But so okay, and then so this is.
But I have one problem.
Just one. That's good. So this is the Hamiltonian that generates squeezing. We understood that it involves creation and annihilations of pairs of photons. We understood why, because, well, if energy from the drive is being converted into energy of the signal, then because of the fact that the frequency is twice, it should somehow involve pairs of photons. And now let's explain a little bit why. That has to do, but before this, let's do another thing, and that is to ask, if I want to talk about things in the Schrodinger picture. Okay, so now from the Heisenberg picture we understand everything. We start from this is how an operator evolves, and we saw how, according to this Hamiltonian, the operator A will evolve into this this A. So this part we're happy. Now how about what happens, but we know also that the state psi at time t is related to the state psi at time 0 by the time evolution operator, which is e to the minus I h t. But this, we know what it is. Okay? This guy. So e to the minus I times e to the I. So we have here kappa alpha pump a squared minus a dagger squared operating on psi. We can call this the squeezing operator because it takes a state and generates a squeezed state out of it. So, and as you know, if I want to calculate, I can say this. This is S. And usually this is what we call G. So S of G. And this is the squeezing operator. Now, let's do ourselves a favor. Okay, it's hard to understand what it is. But let's think what this does to the vacuum, and then we'll see that it makes sense. So, let's try to look at what happens when we apply S of G on the vacuum. Now, what I need to do is to write a series of the, if I want to understand what it is, then it will be 1 plus G times A squared minus A dagger squared plus the series here operating on the vacuum. Now calculating all those, everything higher than here will be complicated, take time to calculate. I'm not going, but let's just think about just this. No, this we wrote, okay. So I'm talking about the squeezing operator that operates on the vacuum. We can do this on any coherent state that we like, but the vacuum is convenient. And of course, that will be, if we do this, we operate this on the vacuum, and that will be vacuum plus, well, A squared operating on the vacuum does nothing, and A dagger squared operating on the vacuum generates the state 2. So plus G, or minus, that doesn't, maybe it does matter, times 2. And then there would be plus something here that goes like G squared, but it's a function that it contains G squared times the state 4. And then, there, okay, and will be many multiplications here, because here for the next thing would be A dagger, A squared minus A dagger squared, this entire thing squared. So what is sure that you will have only even powers will be there, but you'll have here something like A goes A to the 4th and A dagger to the 4th, and something that goes like twice annihilation and twice creation. this will actually correct what we put here. But for now, I'll just throw this one. Okay, I'm just going to look at the first two terms. So first of all, this operator operating on the vacuum generates pairs. You start from nothing, and you have nothing plus 2. Never 1. Okay, so you have either, you remain with a large probability to have no photon, and you have a small probability also to have a pair. It's a superposition of those two. And if you look at the entire series, then you will have, the entire series will look like psi will be sum over n, sometimes Cn, and this 2n photons, where n starts from 0 to infinity. So it's a surprising state. It has probabilities to have all kinds of photon numbers. It's definitely not vacuum. If you put the detector in front of it, you will see some probability to detect 2 photons and some probability to detect 4. If it's a weak squeezing, if G is small, then you can cut the series here, and you have primarily vacuum and some probability of detecting pairs of photons. It's not vacuum. It's not a vacuum state. But we call it squeezed vacuum. Why? Well, because we operated this squeezing operator that we derived from what we said before, but there's even more to this. Let's think about this. Let's go back to those states in the position representation. Okay? So if I think about, so here is my oscillator. Here is the vacuum. This is the 0 state. Here is state number 1. Here is state number 2. And of course, there are many states out. And they're equally spaced. Now, the vacuum in the X representation, well, also in the P representation, it doesn't matter in which representation, but it is a Gaussian. So what we have here is a Gaussian sitting around 0. Well, you know how n equals 1 look, but it doesn't participate here, so I'm not going to draw it. And n equals 2 looks like this. Right? It has some here, and then down, back up, and like this. The Hermite polynomials. Now, what will happen if I take this and mix it with a little bit of that? It will either, so depending on the sign between them, what can we have? We have wings of opposite sign to the center. So either I will have more at the center and less at the wings, or the other way around. Less at the center, more at the wings. This state, the result of this two, when I take those two and I sum them up, then I'll get something that is either, if this was, if that's the original vacuum, then I either have something that is more squeezed or shallow. Do you see why? You should ask questions if you don't. So this is what you'll get if you take, no, what I'm saying is, again, think of taking a lot, this, and reducing a little bit of that, minus this. So at the center you'll have a little bit higher, and at the wings you'll have a little bit lower. So this was exaggerated, but certainly the center will be higher and the wings will be lower. We will have something that has a lower extent in x. On the other hand, if this goes with the other sign, then we will have something that is a little bit more stretched in x. Now, again, those states are not eigenstates of the free space Hamiltonian. They're not eigenstates of any Hamiltonian, not even of this Hamiltonian. Because we operated on vacuum. Vacuum is not an eigenstate of that Hamiltonian. It's an eigenstate of the free Hamiltonian. Those states, they evolve in time. How do they evolve in time? Well, you know, as any state evolves in time. If you have this state psi, then as we just realized, this psi is going to be indeed, depending on the relative phase between those two, it can either be squeezed or stretched. And this squeezing is real. It is indeed squeezed. And if you think about this, then psi of t equals what? This sum, Cn e to the I n omega. Sorry. This is 2n, so this is twice. 2n omega t times 2n. Do you agree that this induces that? Or how does this state evolve? It actually evolves as being 0 plus or minus g times e to the I 2 omega t times t2. This is how psi of t looks like. So you see that this state, after it passed through the nonlinear crystal, okay, it exited the nonlinear crystal at some way. Then it's moving according to the free Hamiltonian. It's not interacting in the nonlinear crystal anymore. It was squeezed as it went through the crystal. And now, what does it look like? Well, first of all, it is changing at frequency 2 omega. It has mostly probability of being 0 and some probability of being at 2. As we mentioned, this is assuming weak squeezing. And if the squeezing was higher, then we would have had more weight to higher possibilities, and we would have even further 4 photons and 6 photons and 8 photons. All of those would be there. But, and as we saw, that what it means is that it changes. In the X representation, it is squeezed, and after a quarter of a period, it becomes stretched, and then squeezed again, and then stretched again. This is exactly like the rotation of an ellipse.
אבל לא אמרנו שגם X ו-P בעצמם הם אחד הופך לשני ככל שהזמן עובר, כאילו X הופך ל-P.
It's exactly the same. Right. This is exactly what we're talking about. Indeed, you know, this phase-space representation, you should take it with a grain of salt. But what do we have? We know already that the vacuum is this. And when the vacuum rotates, this is X and Y, and this is the vacuum, so then nothing happens. But now what we just have is this. It's squeezed in x, it's narrower in x, and it's broader in y. And this thing, when it rotates in time, indeed, that's what you see. For example, if I'll ask myself regarding that state, and we will do that immediately, soon. If we ask ourselves, what is x squared when we operate it on, let's call it, let's mark it like this. What's the average uncertainty of x when we operate it not on vacuum, but on squeezed vacuum? The answer is, it will be vibrating. It will be dependent on time. It will be time dependent. And it will go like, times, let's call it x0 squared. Let me just draw it. You know what? It will do this. If this is the level, this is time, and this is what we would call x0 squared, that's what the vacuum would do. It would oscillate from more to less to more to less to more to less of it. At a frequency which is twice the optical frequency. Okay. So that means, and really, if you think about this, this is exactly what happens when you have an ellipse like this that is rotating. So if I ask myself, well, how does if I just measure the field, okay? I try to do this. I measure the field. Now, the electric field is a Hermitian operator. You can measure it. You can do that for the vacuum as well. But, well, we know what we should get on average. On average, it's going to be 0. But it does have some fluctuations, which we know what they are. So the vacuum would be anywhere between those two levels, okay? So we can call this what we call x0, which is basically just half, or we can just define it to be 1. And it can be anywhere inside here. This is any value within this as a function of time can happen. Now, if I think about what happens to the squeezed vacuum oscillates between more and less. The squeezed vacuum does something like this. And if you ask yourself, at this time, where can I find the field? The answer, it can have many values. The average is still 0, but the fluctuation is larger. Here there's more possibilities. That's the squeezed vacuum. Not R, we were talking about G, so let's use G. And here, so it is stretched, squeezed, stretched, squeezed. It's exactly, by the way, what we understood would happen from thinking about the states of a harmonic oscillator, and it's exactly the same as you would expect from having an ellipse that rotates, a probability ellipse that rotates. So all those pictures, so this is when you see the squeezed axis of the ellipse, and this is when you see the stretched axis of the ellipse. And that was squeezed vacuum. We'll talk about squeezed coherent states in a moment, but because it's already been an hour and a half, and we want to have a break because you do seem a little bit tired, a little bit. Maybe I'm reflecting on you, my feeling. So, we understood, so things somehow start to relate. So we understand that, first of all, okay, there is that squeezing, it relates to processes where pairs of photons can be generated or annihilated. And and we realize that, you know, if you can think of this in two ways. One is you can say, look, the operators evolve. So I can look at, say, I can do the calculations of what happens for squeezed vacuum in two ways. I can ask myself, okay, so what is, you know, there's A of t. Now, of course, but that's not the function. So I want to measure some value, f, which depends on A and A dagger, whatever it is, some Hermitian operator that is built out of those guys. And I can, so I call this f of t, the operator f of t, and I can calculate this operating on psi. And that will give me, or I can do the same to say, but we know how f evolves. This is just to say things in terms of this equals f0 times e to the iht, e to the minus iht, and that or this is just or I can call this thing psi of t, and this thing psi of t like that, and then we're back to the Schrodinger picture. So all of those are the same, and this operator e to the iht, when the Hamiltonian is the squeezing Hamiltonian, this two-photon Hamiltonian that is there, this is the mechanism that takes one state and squeezes it. You really want, if you want to generate a squeezed state, take whatever state it was, let it interact with this Hamiltonian for a while, for time t, and you will get a squeezed state. And now we have all the tools that we need in order to do any calculation with squeezed states that we want. And we can do it in the Heisenberg picture, or we can do it in the Schrodinger picture. And let's do at least one calculation. So, yeah. Yeah, let's calculate indeed this operator x squared Yeah. For okay, so I'm wondering if to do that or not. No, maybe we'll leave that as a. Well, you know, this is a plus a dagger squared, and if I want to talk about x out squared, then that would be those. So that is, oh, we know already what it is. We don't need even to write it. It's just x in times e to the g. We've seen that from the very beginning. So this is squared and squared. And this, and clearly, you know what, from just writing it like that, there's nothing to calculate, because x out squared operating on vacuum, this is the Heisenberg picture kind of image, because we are assuming that is e to the 2g of 0 x in squared operating on the vacuum. And this we know what it is, because this is indeed a plus a dagger squared, whatever we can calculate it, but we know what it is. This is what we just, let's call it 1. Or what we call the vacuum level. So in this case, this quadrature, this is the stretched quadrature. Of course, if I ask what is y out squared, that would be e to the minus 2g times 1. The multiplication is still unity, but this one goes below vacuum. There's less noise to it than the vacuum itself. And as we saw here, what we see here is stretched, squeezed, stretched, squeezed, because the ellipse rotates. You see it, the function of omega. Now, I want to draw some. And what about the squeezed coherent state? Let's draw two cases, okay? Now, first let's think about the coherent state. The coherent state is just this, and some uncertainty here. This is the standard alpha. Now, the standard alpha, if I think about this in time, what will it look like? Well, this thing rotates, and there is an uncertainty to it. So this rotation generates an overall sine wave oscillation. This is if I ask myself, what is E? As we said, this is just the average value. There is an uncertainty here. And the uncertainty is constant, so I can draw some kind of an uncertainty, region around this average value, and you could see any kind of, at any point in time, you could see any value of field within this uncertainty band. Now we can ask, well, what about a squeezed coherent state? Those are clear what they are. I mean, this is just, as we said, we can squeeze the uncertainty. The point is, how do I squeeze the uncertainty? We can have, so this is, we can have this, like, so I'll have this, and the uncertainty will be like that. And this would rotate, right? Just as this thing rotates around, this thing would rotate around. How does this rotate around? Then this thing has, look, this thing has a better defined amplitude. Its amplitude uncertainty is less, but its phase uncertainty is larger. So that means that, you know, here's the average is doing the same thing. That's what the average does. That's what the average does. But the uncertainty looks different. Here, at the peaks, it's less. And then here, it's more. You don't know exactly when it will cross zero, because you see this thing rotates and then it becomes again like this. It's funny. This is amplitude squeezed state. Now for squeezed vacuum, this thing doesn't make any difference. I mean, we can talk about amplitude squeezing or phase squeezing. The amplitude is zero anyway, it doesn't matter. But for coherent states, it does change. So this would be amplitude squeezed. The other case is phase squeezed. So this was the coherent state. Amplitude squeezed states. And now we're going to talk about the phase squeezed. This would be y and x. We'll have an amplitude and we'll have this kind of uncertainty. And when this thing rotates, it rotates again. It rotates that way. The amplitude has more uncertainty. But the crossing of zero is well defined. So this is a function of time. I ask myself, what is E and its uncertainty? And again, we have this sine wave that does this. But if I ask myself, okay, so what's the uncertainty here? This one's large. And here, at the zero crossing, somehow it always crosses at a very well-defined point and then becomes large again. This field has a very well-defined phase. Where does it cross zero? I know very well, but I don't know what its amplitude is going to be. And of course, you could have all kinds of rotations, but all those rotations are mixtures of phase squeezing and amplitude squeezing. Yes? Any question? Okay. This amplitude squeezing, let's make it more pronounced. אוקיי.
אתה אומר שאם נעשה אז ניסוי, אז נראה את נמדוד ונראה את אחד, אוקיי?
כן.
דוגמה לניסוי שעושים כאילו כשלראות דבר?
Sure. Well, first of all, this is very real. Okay. So the question was, is this something that you see in experiment? The answer is definitely yes. And to understand how, we're going to discuss interferometers for now. And you will understand, it will take something like, I don't know, probably 10 minutes to introduce the concept, and then you'll see where things come in. Where this comes in. So you already remember an interferometer. You already know about a beam splitter. A beam splitter mixes modes. Parametric amplifier doesn't mix modes. It operates within the mode. It mixes the operator with its dagger. But a standard beam splitter, it mixes modes. And then an interferometer, which is two beam splitters in a row. So then that's easy. You know, I have a first beam splitter, second beam splitter. If it's a Michelson, then it's the same thing, just folded onto itself. And then I have here a mode A. Now we should be careful. We know already, even if I don't put anything from here, there is a mode coming here, and this mode contains vacuum. So we should remember that. Even though, you know, classically we can say, well, I have a field, it splits into two, and I'll calculate. And then here there's going to be some relative phase, relative to this arm, and I'll calculate. But now we should be careful, and we know that there's another mode B. And here, I don't know what comes in here, maybe a coherent state, maybe something else. But here, if this is an unused port, then we must assume that what we have here is vacuum. So this is alpha in mode 1, but 0 vacuum in mode 2. And there will be output. There will be two output modes, C and D. Have some state. Now let's do some calculation about the interferometer for several cases. Okay. Now, what do we measure? We measure usually the output intensities. Between the intensities, there are noises. We can anyway. So we measure the intensities. What do we want to get? We want to infer the phase. Because this is what we want to measure. What we measure, we put here a detector, and we put here a detector. The battery is low again. Those batteries are no one hears, huh? צריך להגיד ליוסי ש... אז לא היית משלם? אבל אמרת שאם זה היה רק אתה לא היית מתלונן.
נכון, אבל בהקלטה ביוטיוב זה גם אותו דבר.
שם זה כבר להיט.
Okay. So what we measure are what we measure is C dagger C, D dagger D, and higher moments, functions and higher moments. But we want to infer phi. So we want to, and specifically, so we want to measure this I, C, and I want to measure those guys, IC as a function of phase, and ID as a function of phase, and I want to invert somehow this function to get the phase out of that. And so let us calculate what happens, how we, so first, let's make the relation between C and D and A and B. Now you already know, we know that what we have here, if this is A and B, then what I have here is A plus B divided by square root of 2, and here is A minus B divided by square root of 2. Now this one gets a phase of phi, so let's write this phi here. And here we have, so this one gets a phase of 2, square root of 2 e to the I phi. This is what we have there. And here it remains the same. And now C is the sum of those, and D is the other sum. We will have here e to the I phi. So clearly what we will have in the end is this. C equals A times sine, let's say C equals A times cosine phi plus B times sine phi, and D equals what? מה איך? נצא. תכף מיד אני אסביר לך את התיקונים הקטנים שהיו חסרים כדי להשלים את זה, אבל and this one will be, sorry, not phi, it's actually phi over 2. And D equals what? B, sorry, not B. A times sine phi over 2 minus B times cosine phi over 2. What? I? No. No I. Yeah, but there is an overall phase that I neglected. What I wrote works if you assume that there's a phase phi here, and then minus phi on the other side. Then everything's fine. No, this one is right. Or we can say that in general, the modes C and D are related to modes A and B by a matrix, which is cosine phi, sine phi. Now here, I wrote it like that. Usually the relation to do is like this, plus here and minus there. No, is that right? What? And of course phi over 2. This is, so what I want to tell you is, look, what's the problem? לא.
מה שאתה עושה, אתה פותח את האקספוננטים, אתה עושה פלוס אקספוננטים ומינוס אקספוננט. המינוס יצא לך I כפול החלק הג'נרי.
Okay. Wait, there are many ways to look at an interferometer. eventually all of them come down to seeing this matrix may be multiplied by an overall phase. The matrix is always the same. Now, if it is multiplied by an overall phase, let me just remember. Yeah, that is true. Yeah. For example, when the phase equals 0, then C equals A and D equals B. When the phase equals 180 degrees, or the phi over 2 equals pi over 2, then you sweep them, you swap them. A goes out to C and B goes out, well, the other way around. A goes out to D. You swap them. And in between, you mix them. So actually, if you think about this, this is basically a beam splitter. The entire interferometer acts like a beam splitter whose reflectivity and transmissivity depend on the phase. Okay? So this is like a beam splitter with R equals cosine phi and T equals sine phi, or the other way around. And because R squared plus T squared equals 1. It is a lossless device. So that's something to remember. Now, using this relation, we can now do any calculation of the output depending on what we assume on the input. So let us calculate, for example, C dagger C average. When we assume, so we're going to calculate the intensity in port C as a function of phi, average, assuming alpha at port A and vacuum at port B, which is the standard way to go. So there's a coherent state, maybe large, in mode A and nothing in mode B. I want to calculate this, and well, that would be easy. And C dagger C, well, now what that is A cosine phi. Of course, it's not phi, it's phi over 2, but if I go continuously, well, okay, we'll keep it, plus B. So this is dagger and dagger. Sine phi over 2 divided times A cosine phi over 2 plus B sine phi over 2. Now the point is that this is going to operate on alpha in mode A and 0 in mode B. And there's alpha and 0 on the other side. I just don't have space. No, I'll write it downstairs. So if we look at C dagger C operating on alpha and 0, A and B, well, you can see that the only thing that would matter would be anything that operates on vacuum annihilates. So the only operator that is going to survive is the A dagger A times cosine squared. Do you see it? Well, you see other things right now, so you don't see it. But you watch the movie 50 times, and then you see, I switch.
Because he was late after the break. So.
Exactly. So that would be, so we'll have here basically A dagger A on alpha and alpha. This will be the only thing that will contribute. Sorry, and there's this cosine squared. So we're going to have absolute value alpha squared times cosine squared phi over 2. I guess you'll believe me. And this actually, well, that makes sense. You know, either the entire intensity goes out that port, or nothing goes out of port, and it oscillates. That's what interference does. And I am sure that you'll believe me to see that D dagger, D average, would equal the same thing times sine phi over 2, sine squared. And the total intensity should be 1, because this is an energy preserving thing. But, and now, good. And if we take, for example, indeed this IC minus ID, the average part, so the average difference between those two, then that would be alpha absolute value squared times cosine squared phi over 2 minus sine squared phi over 2, which is cosine of phi. If you, well, you should remember trigonometric formulas. This is the basic equation of classical interferometry. Here is how we extract the phase out of the intensity. It's an oscillating function of the phase. And now, so if this is the phase, this is the intensity, and what I have, or the intensity difference, and what we have is just an oscillating function, the phase phi. Now remember, this phase phi is not the field phase. It's not the phase of the field. This is the phase of the interferometer. This is just the length difference between the two arms. And just to make sure that you're not confused, this length is not an operator. This is just a parameter of an interaction. Just as location for the field is not an operator. Position, where I am in space, this is not an operator when we talk about the field. The field operators, the space, the Hilbert space in which the field is an operator, is not real space. But, okay. So now, you see this, and now I ask you, where, suppose now that I want to measure some small changes of the phase. Oh, no, we already did that. So now I'm going to tell you, yeah, we're going to talk about the sensitivity to phase. So, I park at some Now, what I measure, I know how to so I know I can measure this intensity difference, and I want to ask myself, well, what do I see? So, well, the answer is right now, that's simple. You just need to say, what is the phase? Well, that's invert that function. So you measure delta I, you know the intensity of the light that you throw in, and you extract the phase. Now, what if, the experiment is not perfect, and there is some noise in the intensities? So that this intensity difference, it's noisy for some unknown reason. Now, it really is unknown. What do I mean? Because classically, if you think about this, classically, if you throw in, I don't know, whatever intensity is here, and nothing here, so here there's really nothing, this is 0. And then what comes out at the output? Well, whatever it is, it's multiplied by the same intensity. So if I talk about, and specifically here we talk about the difference. So the difference of intensity that, for example, okay, so here, when I'm here, what do I expect? Okay, I have something that has some intensity noise. Okay, so when all the intensity goes to port A and nothing goes to port B, or sorry, C and D, then I would have some, if this intensity is noisy, then it's a multiplicative noise. So it looks like this. Here there is maybe an uncertainty, but here, when the two intensities become equal, you have 50-50, you're dividing the intensity 50-50. So those two halves are equal. It doesn't matter if the half is growing large or small, but the difference is still half. Sorry, not half. They're equal. So you expect something like this. This is not squeezing. I'm just assuming that here there is an uncertainty. Something. So this is the classical prediction. Classically, and then you can ask yourself, okay, so I'm going to ask about the sensitivity to a phase. What do I mean by the sensitivity to a phase? Tell me, now this is really simple. If you have, some value, I don't know, some function, f, that depends on some parameter, phi, and you measure f and you want to estimate phi. So if f is fluctuating, this would induce fluctuations in phi. According to what? Well, df to d phi. So I can say this, delta f equals what? df to d phi delta phi. So that means that if you want to know how much uncertainty in delta phi you have from the fact that there is an uncertainty in what you measure, then this is simple. Delta phi, or let's even say, make it small delta, because this is assuming a small parameter. So delta phi equals delta f divided by df to d phi. And now these are fluctuations. This is the relation between fluctuations. And if I ask myself, and what about the second moment? So delta phi squared average. The average fluctuation in delta phi is related to the average fluctuation. Yeah, let's do it like this. Delta phi squared average is related to delta f squared average divided by this absolute value squared. Now this tells you, you have some parameter phi that you want to estimate from the f. Tell me then how much noise there is to f, just from problems of your instrument, whatever it is. And I'll tell you how much uncertainty you have in phi. For example, if I sit here and then, there is this uncertainty in the intensity here, then, I don't know. Well, I should have drawn a smaller uncertainty because things would now become too large. But that means that maybe I am, so the intensity is fluctuations between these values. So that means that I could be anywhere between those two phases. Why? Because this is where, this is where I'm drawing. You understand what I'm drawing here? I'm assuming the average. What can I do? I'll assume the average, and then there's fluctuations around it, so that will cause me a mistake that has to do with the derivative. That's all there is. But clearly, from a classical thinking, here, there is no uncertainty. At this point, this is where the two intensities are equal. Exactly. It's a 50-50 beam splitter. Classically, it just divides the intensity by half. So if we think about measuring around a phase of pi over 2, we expect to have infinite, or not infinite sensitivity, but zero sensitivity, maximum sensitivity. You will be sensitive to anything. And just to make clear what we see here, this result is basically taking we have two intensities, one that looks like cosine squared. This is IC, goes like cosine squared phi over phi, cosine squared phi over 2. And there's, and this ID goes like this. Is the most sensitive location to measure. That's where the intensity. Now look, I've done this too many times. מי המנחה שלך? דוד?
כן, כן.
נדמה לי שאתה בהנדסה, לא?
בסדר, קצת...
הומור עצמי, הומור עצמי. כל פעם אני גומר עם איזה ציור על החולצה. Okay. So it makes sense that you want to measure around this point. Now here comes, so now comes the, oh, no, it's a big shock. But now let's think about what happens quantum mechanically. And the main thing that we want to now calculate So that was the average, and that is the point. Classically, there's only an average. Quantum mechanically, there's also quantum uncertainty and there's quantum noise. So if we want to calculate this, then what we need to put here, we need to calculate that. So now we want to calculate this, what we had there, IC minus ID. This is the operator that we have. I want to calculate that squared and have that. This is what we need. We need to calculate the noise.
So it must be called Shulash.
What?
זה גם פחות המומנט הראשון בריבוע.
כן, אבל המומנט הראשון, okay, we'll see. We want to look here. And here the first moment is 0. Yes. But the average we found already. So this is what we want to calculate now. This is what we need to calculate. Okay, so now we want to ask ourselves, what is C dagger C minus D dagger D squared? Okay. Then we will have to, so this would be, yeah, so this is, it will take, you can calculate this, and now you need to believe me, because we're at the end of we're really at the end of our meeting. What? But yeah, I mean, we want to finish this. Let me tell you, I don't see pizza as food at all. I mean, and I'm not only vegetarian but also vegan. So you know what? We will celebrate with broccoli. Okay? האמת? נעשה, כן, פודינג צ'יה זה ממש טעים.
או, יש לך רעיון מההרצאה.
או, כן, או איזשהו קינוח טפיוקה עם קוקוס ו...
עושה את זה מגניב ככה בגליל.
זה הרצאות תמיד של למה חלב.
אפשר לעשות את זה תכלס עם צ'יה. צ'יה באמת...
עושה את זה ככה, כמו סינוס, תעשו את תביא לנו אותו.
That's enough. Okay, yes. So, let's, first, the main thing is that if we calculate just this, you know, I'll just whatever is here, this C dagger C minus D dagger D, and I'll tell you what that is. This is, it comes out to be cosine phi times no, wait, sorry. Okay. I don't have it written, and I don't want to do it on the board, and it's late. So we're going to rush it really quickly. So we can do this. We can calculate that and use C equals A cosine phi over 2 plus B sine phi over 2, and the other one, and we can put that in there and calculate this. But I want to tell you that you don't need to. Why? Yeah. Maybe we'll do it next time. But because we're already late and we will really finish this calculation next time, so let's see a little bit of intuition to where this thing is going to. Because I promised something, but then I was tired, and then people asked me to replace batteries all the time. And then, so this is why, David, it's your fault that we didn't get to the point. But where is the point? The point is this. Let's think about what happens. We were thinking about this point of what appears to be the best sensitivity. At that position, what is happening in our case? Here, no photons coming. There's zero. Here, there's a coherence state. Now, I don't know exactly how many photons come in, but on average, alpha squared. And those photons are now being split between those two detectors. Equal, 50-50. This is what this point is. This is the position where photons coming in from here split exactly equal. So now, and then we want to infer from the difference the phase. But here is the point. This is like a beam splitter. What is a beam splitter to a photon? It's a coin toss. So we are throwing n photons into the interferometer. By the way, we don't know exactly what is n, but this part doesn't matter because this is common mode. If n is 100 or 105 or 103, it doesn't matter because that's what we threw in. This is going to divide. That's how many coin tosses we're going to make. So on average, we're going to make 100 coin tosses. But what are we going to get? We're not going to get 50-50, and we're not going to get half and half. It's not going to be always. So there is going to be an uncertainty that has nothing to do, that's only from the quantum nature, from the fact that those are coin tosses. So if I measure those two intensities, I classically expect to see exactly the same. And quantum mechanically, I do not. Because I'm throwing in, on average, 100 photons, but I don't get exactly equal copies. But there are fluctuations in those intensities. And those fluctuations are fundamental. They are there. Well, why are they there? Because this port has vacuum in it. And this vacuum is not zero. And this is what we'll do next time. We'll calculate this for the case where what we put in is a squeezed vacuum. And we will see that exactly this number difference will be reduced, will be less. So this squeezing that we had, the fact that the squeezed vacuum can go below the vacuum uncertainty. If you use a squeezed vacuum and you feed it to the unused port of the interferometer, and you choose the phase wisely, the phase of the squeezing, so that you align the phase of the squeezing such that what you will see, this will cause this difference to become, of course, on average it will be zero, but its fluctuations will be smaller. And therefore the inferred phase will be more accurate. That was a little bit hand-wavy, but all of this will become much clearer in the beginning of our next meeting. So our next meeting will finish the discussion of interferometers like this. We'll understand how squeezing helps. And then, I don't know, we'll do something interesting. Yeah, I think we'll talk about the Jaynes-Cummings model. We're done. Do you have any questions?
נדבר על לייגו?
Do you want us to talk about Ligo? Well, we just did, didn't we? No, we will talk about Ligo. Yeah, I mean, and for our last meeting, we'll have I don't know, requests from the crowd.
יום טוב, ביי.
Arrivederci.